Okay, good morning in the United States, good evening in Nepal, and at different times elsewhere. So thank you everyone for coming to the session of Physics Education Research presentation. So today's presenter is Professor Beth Thacker from Texas Tech University. Professor Thacker has developed a laboratory-based, inquiry-based curriculum taught using Socratic questioning pedagogy, and has done significant work investigating students' qualitative and quantitative understanding of physics concepts in courses taught by traditional and non-traditional methods. She is presently working on a student understanding of quantum computing concepts, graduate student understanding of symmetries in classical mechanics, a project using augmented reality to enhance physics instruction, assessing pedagogical content knowledge of learning assistance and assessing student thinking skills across pedagogies. So today, Professor Thacker will be presenting on development and research of an evidence-based, laboratory-based physics course for algebra-based physics students. So with that, I would like to request Professor Thacker to start her presentation. Thank you so much for accepting our invitation. Like, this is Association of Nepali Physicists Physics Education Research Division. We recently started this. Actually, we started this innovative teaching and scholarship of teaching and learning 2 years before, but now we have established this new PER division. So please, Professor Thacker, now is your time. Thank you.
Okay, thank you, and good morning or good evening to everyone here. And I'm glad you're interested in PER now. That's exciting. I'm going to tell you some about this course we developed. I understand that you did talk about one of the papers I wrote on it already. So I thought that I would talk about the course and about research done in the course, but you should feel free to ask questions at any time. You don't have to wait till the end. So if I'm talking about something and you want more information at that point, go ahead and ask questions. So let me get started here. If I figure out how to do this. Okay, why am I not moving forward? Let me try something else. Oh, that works. Okay. Okay, so this course was developed it's almost 25 years ago now. And what happened at the time of development, things that existed in physics education and physics education research were, first of all, physics by inquiry, which was a course like this for pre-service teachers at the University of Washington. And also workshop physics existed, and it was for calculus-based students. And so part of the reason for the development of this course was to see if we could do something similar in the algebra-based course. So could we design an algebra-based course that was taught without a text, based on experimentation, where students work in a laboratory environment all the time in groups, it's hands-on, and we wanted to do it for the algebra-based course. So it has a lot of, excuse me, similarities to both physics by inquiry and workshop physics. And it is what I said, students work in groups, it's laboratory based, it's hands-on, there is not a lecture, we don't ever lecture, there's not a required text. Students work through the materials that we've developed, and then we use Socratic questioning as the pedagogy. So what that means is instructors, which are faculty, graduate students, and at this time, since we've expanded, learning assistants who are undergraduate teaching assistants. We circulate around the room, and at certain places called checkpoints, we talk to the students, and basically we start by asking them questions to see if they understand what they've done and understand the concepts or the skills that they should have learned at that point. Okay, so this is what the course is like. The students are mostly health science majors, so they are pre-med, pre-dentistry, pre-physical therapy. They want to go into some kind of health sciences for the most part. There's some very interesting facts about this group of people. I'm going to drink some water here because my throat is getting sore. Hold on. Okay, so these are just interesting facts about the group of students. The mathematical knowledge is wide. It ranges from struggling with algebra to understanding calculus. And it's about as broad as you can see in any physics course. So some people haven't had math since high school, and now they're juniors and seniors in college. And some people have had at our university what we would say calculus 3. So they've had 3 courses in calculus. So it's a very wide range of math. The other thing that happens is most of our students are juniors or seniors, and it's a freshman, sophomore level course, but they're afraid of physics and they put it off. They don't want to take it till they're about ready to graduate is what happens. So we have juniors, mostly juniors and seniors in a freshman, sophomore level course. The population is about 50% male, 50% female. This sticks out because that's not usually the case in physics, but it is the case in the health sciences. So it sticks out in a big way if you're used to teaching physics courses. Usually, this is the only physics they're going to see, these 2 semesters of algebra-based physics. And about, well, actually more than 10%, minimum of 10%, will be taking admissions tests like the MCAT, the medical college's admission test. There's also one for dentistry and physical therapy school. They all have their own tests. So that may or may not be an issue. When we developed it, we would say our theoretical framework is constructivism. And basically, I would describe it by the knowledge is constructed by the learner. So some people say nobody teaches anyone anything of significance. The teacher is the guide, and the student has to construct the knowledge. So learning is an active process. It's also a social activity. And the mental models that you develop, they're personal. And people are always changing their mental models and integrating their new knowledge and their new experiences. What just happened here? Okay. How do I go backwards? Okay. I need to be, there I am. Okay. Okay, implications for teaching. Teaching is not transmission of knowledge. It's not what we call a sage on the stage where you just dump knowledge into a student's brain. The student actually has to do something in their own brain. The instructor also needs to understand the student's preconceptions in order to guide them to a scientist's conception. Learning is an interactive experience, and students must be active in the process. And students need time to reflect on their new experiences and build new cognitive models. So after we had developed a course, the main question is basically, is it going to work? And what would be the benefits and drawbacks of such a course? And so our research questions evolved mainly into these 4 questions as we went through the years. How does the inquiry course compare to the traditional courses? How do the thinking skills of students taught traditionally compare to thinking skills of students in the inquiry-based course? Can the course successfully be expanded from sections of 24 to sections of 60? So we started with 24 students and now we're up to 60 students in a section. And can we evaluate the learning assistant's pedagogical content knowledge in the context of a Socratic questioning pedagogy? So these developed over the years. So I'm going to go through them kind of sequentially. And I'm going to talk first about early assessment, basically. And the data I'm going to show, though, is from a large-scale assessment we did where we compared the inquiry-based course to traditional courses. And so as part of the course, we administered conceptual inventories, which like the force concept inventory, MBT, mechanics baseline test. BEMA is brief electricity and magnetism assessment. CSAM, I'm trying to remember what that one stands for. The ENM is electricity and magnetism. I'm forgetting the CS right now. But it's another one on electricity and magnetism. So we administered these both in our algebra-based and calculus-based courses here at Texas Tech University. And so okay, I'm sorry, I'm just having trouble getting forward by one slide. Let me try this. All right. So this is what happened in the algebra-based courses. So the inquiry class is the top one. The second line, the purple line, is where we had an instructor teaching. I would say the lecture was based on physics education research, and the RT is for laboratories, which were also based on physics education research. So they're real-time physics laboratories. And it was very interesting to see that these two lines were not distinguishable, basically, if you look at the uncertainty. And the others were either traditional lab or traditional lecture. So the third one, the green line, was a research-based lab, but a traditional lecture. The red line was the traditional lecture, but with the real-time physics research-based labs. And the lower blue line was when everything was taught traditionally. But the main thing that stuck out to us was that the top two were not distinguishable. And we actually have data of the same instructor teaching an inquiry and teaching a traditional section at the same time, the same semester. And the conceptual inventory data was not distinguishable. And that was very interesting to us. Let me show you one more piece of data before I go on. For BEMA, our scores are always low. I don't really have good comparisons across the country because I'm not sure that many people in the algebra-based course run BEMA. But we have low scores, but ours again are higher than the traditional sections. And again, the inquiry is not distinguishable from a traditional section using research-based materials in lecture and lab. So this was really interesting to us because then the first question that you might ask is, why are we even teaching by inquiry if it's the same as traditional sections that use research-based materials? So why bother with this course at all, this different kind of teaching? And what we thought about is that it's probably thinking skills, or at least has something to do with thinking skills. So we wanted to start researching that. So how are the thinking skills of students taught traditionally the same or different from students in the inquiry-based physics course? So we started to research that. And the first thing we did was we developed a rubric and we based it on Bloom's taxonomy. And I'll show you the levels in a minute. And then after we did that, we identified common quiz and exam problems, both from historical classes. We have historical data in both classes and recent data of classes taught by different pedagogies. And mostly we were looking at the inquiry-based sections versus lecture sections, traditional, totally traditional, or lecture sections based on physics education research, which might be interactive engagement sections, but taught in a more traditional setting. So we went through the data we had, but let me talk about the rubric first. We ended up with a 5-level rubric. Bloom's taxonomy actually has 6 levels, and I'll put it up in a minute. We collapsed 2 of the levels because we couldn't distinguish them, and we added a 5th one, which I'll talk to you about in a minute. So when we were coding, the student was simply given a 1 or 0 for each level for each part of the problem as we coded it. And then we assessed inter-rater reliability using Cohen's kappa. So this is Bloom's taxonomy. I guess this is the revised version. It was the one we were basing it on, though. So the lowest level is remember, and then understand, apply, analyze, evaluate, and create. We could not distinguish between apply and analyze when we were looking at things. So we collapsed, apply, and analyze. We also saw very little evaluate and create, but we left off create and left in evaluate. And so let me show you what we ended up with. We added a fifth level because we found there were some people that they didn't answer the question, or it was totally incorrect, even though they wrote something down, or they just wrote down a statement like it fell or it dropped or something. And then we ended up including partially remembered facts and concepts. So those we counted as none. It was our 0th level. So that was our none level. So their answer didn't contain any physics, and it didn't contain things basically that made any sense, or it was totally incorrect, or just a statement, which was not an answer to the question. Okay, so the next level was remember, and here we included a recollection of facts. So here it was, did they recall facts that they needed in order to solve the problem, or concepts? And it was fine if they stated it either mathematically or in words, if it was just a concept. So if either of these existed, we counted it as remember. The next level was understand, and this was that their solution included a correct application of the facts or concepts that they had recalled. So can you go beyond a recollection of the concepts or facts, and can you use them either mathematically or verbally to help solve your problem? Then it's like I said, we collapsed, apply, and analyze. And this was then, did you demonstrate a valid, logical, and consistent process for determining an answer? So applying numbers 1 and 2, you're remembering and being able to use the concepts to achieve an answer. Okay, so the last one was evaluate. We saw this sometimes, but not as much. This is where you justified your decision, or you looked for, does it make sense? So if you stop to think, okay, I got an answer, does it make sense? That we counted as evaluate. We were looking at exam problems, and the fact that we saw basically the lower levels and not the higher level, that actually makes sense in the context of an exam, because in an exam, when you get the answer, you're done and you move on to the next question. So a lot of times you don't stop and think, does my answer make sense or not, or do some kind of higher level creation. So we didn't see the higher levels of Bloom's taxonomy on an exam, but it didn't really surprise us. So this is just a sample problem. It's an E&M problem. So there were charges at 2 positions. The A part of the question was conceptual, or, I mean, yes, you could do it mathematically too, but you could do it conceptually. Is there a position along the y-axis that the net electric field would be 0? And they had to explain their reasoning. The B part was more calculation. If there is a position, determine where the location where the net electric field would be 0 and show your reasoning. So this was common in most of our problems. We usually have a conceptual part and then a more quantitative part. And so let me show you, this is when, after we use inter-rater reliability, we used Cohen's kappa and to see if there was agreement. And so in this particular problem, it was above 80, which is considered by Cohen's kappa to be almost perfect agreement. So data look like this. The blue is the inquiry and the orange is a traditional class. So you can see that the inquiry did better in most things. So the none was where they didn't write anything down, but then we see the remember, understand, apply, analyze, and we did see some evaluate in both classes, not a lot, but that was common among the problems. This was the B part of the same problem. So again, the inquiry class was doing better than the traditional class. And this was a common thing we saw. So this was one particular problem, but across all the problems we analyzed, the inquiry students consistently demonstrated the use of thinking skills that we coded at least as often and usually more than the traditional students. So by our rubric and what we saw, the inquiry-based students were doing better in thinking skills. So I'll go on from there. Okay. So the next thing that happened in this course was in 2018, the chair at the time agreed to expand this course, and he did it by redoing what was a lab in the physics building. And we turned it into a studio style classroom, which could hold 60 students at a time. And with this expansion, a lot of things had to change. We were moving from 24 students in a class to 60 students in a class. And we needed to bring in learning assistants because previously we just had one faculty member and one graduate teaching assistants in the classroom. And so we added to that 3 to 4 learning assistants. And then we also had to train learning assistants. So we have a prep session each week where we train learning assistants. It goes on for 2 hours because we find that learning assistants need to review their content mostly, but we also have to work on how to teach by questioning with the learning assistants. So with this expansion, we added learning assistants. And the interesting thing about our learning assistants is that they have not had any physics course beyond the course that they're teaching. So they've had 2 semesters of algebra-based physics and not higher levels of physics. And that's interesting because you recognize the need for higher level physics because the TAs and the faculty have higher level physics, and sometimes that's important in the classroom. But they do pretty well. And so we have this 2-hour training session each week. And we're using students who have taken the course. Like I said, occasionally we don't have enough of them because you have to want to do it and it has to fit your schedule, and it's a complicated thing to get enough learning assistants. So sometimes we use physics majors, and they're more like the TAs. They have a higher level of physics, but they have usually not been taught in this format. So we're working with them too. It works pretty well. Okay. So basically, though, we don't know how well they do. I mean, we're in the classroom with them, but I can't stand over every learning assistant all the time and see how they're doing. So we don't have a good check on how well the learning assistants are doing when they do checkpoints with the students. We have an idea. We check with the students. They have to check off in the lab manual, they check off that they signed off the students. And so we have checks on them. But basically, we don't know how well they're doing. So that led to more research. So the research questions for this part of the project was, how well can the learning assistants who have taken the course but are not physics majors teach by questioning? How well can our graduate TAs and undergraduate learning assistants who have not taken the course in this format, but presumably have higher content knowledge in physics, how well can they teach by questioning? And what evidence do we have of their content knowledge, of their ability to guide by questioning, and of their knowledge of students' difficulties? Because they need to understand the difficulties that the students have. So we set out to research this. So the first thing we did was we videotaped them in the classroom. And we did this using something called Swivel, where they wore a mic and there was a camera that basically followed them and connected to them so you could see the video and simultaneously hear what they were doing when they did what we call a checkpoint at a certain table. So we used these videos, and then we watched the videos and we classified our observations based on the videos. And we first did what I call a microscopic coding. We looked at the questioning patterns, and we came up with basically three kinds of questioning patterns, and then one about straight tutoring or lecturing. So guiding questions was the type of questioning that we were really interested in, would like them to do. And that means that you're good at guiding the students through questioning, either guiding them first to draw out their understanding and then guide them further through questioning to come to a conclusion or to evaluate the experimental evidence or to solve a problem. But you do this predominantly by questioning. It's not that you don't ever tell anything, but we focus on the ability to do this by questioning. The second category was probing questions. And so this is just, it's a not quite as high a level as guiding questions, but it's often necessary. So it's like the examples. I mean, why did you drop it from this height? Or can you tell me where you placed the magnet? Or did you take data on this particular thing? So it's trying to find out what they did or didn't do while they were doing an experiment or solving a problem. The last one is checking questions, and those are just basic questions to get at things that they might have skipped, like did you zero the sensor? Or after everything was done, does it make sense to you? And then the last part is tutoring or lecturing. And we all, including the LAs, do this sometimes in conversations with the students. But we did not want this to be the predominant method of instruction. We wanted it mostly to be questioning. And so we saw, well, you'll see this when I go further, we saw them doing different things. Let me go on to the next part. This was saying that the guiding questions is the ones that were most interesting to us because this is where we thought we had the most evidence of PCK in the context of questioning. So we then developed what I called our macroscopic coding. And here we labeled things QA, QB, QE, DA, DB, DE. So the QA level was the instructors who were very good at using guiding sequences of questioning. The QB level were, and this is actually where most of our learning assistants ended up. They understand that they're supposed to be leading by questioning, guiding by questioning, but they fall into lecturing or tutoring at some point. Or they start out lecturing and tutoring, and then they think, oh my gosh, I'm supposed to be asking questions. And so they flip and they start asking questions, which is a good thing. So this is people who have an understanding of what they're supposed to be doing, but it's not actually, it doesn't actually work out that way all the time in the classroom. DA was if you're tutoring or lecturing. And this is not necessarily a bad thing. So the DA is tutoring or lecturing like we would imagine a lot of our graduate teaching assistants do in office hours. They often do tutoring or lecturing, but they do listen to the students and they do question sometimes and they have some idea of the student understanding. DB was when you're basically lecturing and talking at students without really paying attention to their understanding or if they understand you, or you're just talking at them and you don't really interact with them that much. So this was what I called our macroscopic coding. After we did the coding, we were trying to develop an instrument. Oh, I probably didn't say this. Let me back up a minute. We were trying to develop an instrument to measure the LA's questioning ability because we could not always observe it in the classroom. And so we did this by videotaping them and seeing what actually happened in the classroom. And then we turned these into questions that we wanted to put it on an instrument to use with the LAs to get some input on their understanding. So the way these questions were developed, we first did an open-ended question, and then we did this one, which is a prompted question. So the last two questions at the bottom are prompts. So what we did was we wrote questions that gave a classroom scenario. So this question is not about a physics question. What's the physics question the students are working with, but the scenario is what students are doing in the laboratory, either solving a problem or doing an experiment. In this case, it looks like they are solving a problem. And then basically we asked the LAs, what would they do in this situation? What can you conclude about the information provided about the student's content knowledge, the way the students entered this question? What were the students thinking? And then how would you respond to the students? What would you say? What's the reasoning behind your response? And so we developed a set of questions like this, and we actually have a whole set of questions like this that we then gave to the learning assistants. And we did this at 2 universities, our university, Texas Tech University, and Florida International. At Texas Tech, we administered the assessment questions for the learning assistants in sets of 3 to 5 questions. And we did it about 4 to 5 times through the semester. And we did it roughly at the same time the content was covered in class, and roughly the same time they were being videotyped with their answers. And then FIU is a little bit different. TTU was just before COVID started, actually was the semester that we were half in class and half COVID. It was the beginning of COVID. FIU was during COVID. It was 2 semesters that were taught online. And so theirs was all on Zoom, and they had 1 to 2 questions administered each week. And so the I just said the free response questions roughly at the same time they cover the concepts in class. And we coded the free response questions by the same rubric as the videos. And this allowed us to validate the free response questions based on the videos. So we demonstrated criterion validity of the free response questions by comparing the video coding to the free response coding for each learning assistant. The videos, we had lots of videos. So we randomly selected 1 day of what we call vignettes, which were, the vignette is a time period over which they're talking to one group of students. And we selected 1 day each week, and then we averaged the percentage of occurrences of each PCK level for that day and averaged it over all the weeks to get the numbers I'm going to show you in a minute. And the free response questions, we just determined the percentage of occurrences of each level across all the free response questions. Okay, so then we compared. So let me tell you the kind of things we saw. This is TTU, this is spring 2020. The level at which we saw agreement was usually across categories. So for instance, the top student, AF, the questioning is in the video is either QA or QB is dominant, and that's also dominant in the written. So it's not always exactly the same percentage, but the same categories were dominant in the written and the video. And so, yeah, the next one, TZ, was dominant in QB and DA. Those were dominant. And they were similar. So it's not like a direct agreement, but usually the dominant categories were the same. We saw the same kind of thing at FIU. This is just with 2 students. So the first student was dominant in QA and DA, and the second one, mostly DA, I guess. But you could usually pick out 1 or 2 dominant categories. I think this one was a less better match for this fall of 2020, but I think it still works out in a similar manner. Usually you can pick out the dominant categories. So that's the extent to which the video matched the written assessment. So the written assessment then would give us a reasonable idea of the dominant categories. That's what we would say about our instrument. And that, I think, is like the final kind of assessment we've been working on. And so basically, I'll leave it with a summary of that project. We've developed and validated a set of questions that can be used to measure learning assistance PCK. These questions, you could use them as an assessment to inform instructors about their learning assistance PCK. Or you could use it for training purposes, like in your lab prep, give them to learning assistants. And we also found for our present learning assistants, they're mostly at a QB level. So they understand the importance of questioning, but it's not always the only thing they do in the classroom. It doesn't always play out that way in the classroom. I think that's perfectly understandable, actually, for the level of our learning assistants. So let me, at this point, just see what questions you have. Open it up for questions, and you talk to me and tell me what else you'd like to know or what questions you have.
Thank you so much, Professor Thacker, for this outstanding presentation. If there are any questions from any one of you, please unmute and ask to the speaker. Thank you.
Okay, I have a question.
Yeah, please go ahead. Thank you.
So it looks like it's interesting in the sense that you also did this during the COVID period versus the non-COVID period.
Yes.
So I'm guessing yes, it was for the LAs, the study that you were doing, but I'm guessing you were also teaching the classes at that time, right?
Yes.
So how much difference did you find? Did you collect any data and compare, like when you are doing the teaching same method, at least how much we could do, right? During the
Yes.
COVID period, and I'm guessing that is through the Zoom or something like that versus in person. Any did you collect any data and make any observation and found any differences?
Yes, we did actually. We were always doing the conceptual inventories, and they actually didn't change a whole lot. But what surprised us and a lot of other people when we presented it, and we actually have a paper on this, we looked at the critical thinking skills comparing. It's actually not COVID versus non-COVID. Let me tell you what happened. We went back in after a year and a half. We went back into the classroom, basically. So it was still COVID. It's like, how do I explain this? What did we have? Like 2.5 years of COVID. Well, the first year and a half of COVID, we were online, but our university went back in to physical classrooms during the third year of COVID. And so we had data for that year in a physical classroom. And we looked at thinking skills that year compared to online. And what surprised us and a lot of other people is that we didn't see that much difference in thinking skills in the inquiry-based class. And that actually surprised us because we thought things were different when they were on Zoom, and they were. It was very different. But the fact that we didn't see that much difference in thinking skills surprised us. On the other hand, our interpretation while we were online, my personal interpretation, it was horrible. We took this online, we took a laboratory-based class and put it online, and we did the best we could. We had to use simulations, we had to use pictures, we had to use all kinds of things. And when we were teaching it online, it was horrible. Also, the comments from the students were horrible. But when we looked at their thinking skills in particular, they actually weren't that different. So while it was uncomfortable for us online and for the students, and we didn't like it, we did not see that much difference in thinking skills. So that was surprising to us and also to other people. And we do have a paper on that. I'll have to dig it up and send it to you. So that we did research, yes.
Okay. Thank you so much. And here is a question from Suresh Gyawali. He's a student at Georgia State University. Thank you for the great presentation. What are the most recent techniques you are employing to teach undergraduate labs at Texas Tech University?
Okay. Well, this course I'm talking about is basically a complete lab course, and the pedagogy is questioning or Socratic questioning. But that's just this course. The other labs, I have not been that involved with. Now, I was involved in writing the materials about 10 years ago, though, and I'm not actually sure how much it's changed since then. So what we did about 10 years ago in the traditional labs, we put what I'll call a PER section in. It was a section, a qualitative section based on PER research. So in our traditional labs, we had a part where it was very qualitative. It wasn't a rigorous lab like all about measurements. And the questions, and there were experiments, it just wasn't rigorous data collection, were based on PER and to help students understand. But then the second section was more like a traditional lab where you took a lot of data. So we have a set of traditional labs that were written that way. And that happened about 10 years ago. It's like I said, I actually have not been as involved in those labs at our university. So I do not know if people have been using them correctly or not in recent years. But we did write them that way. So that was the intent.
Thank you. Thank you so much. Any other questions?
Okay,
Yes,
I have a question.
Yeah,
That's
please.
a pretty excellent presentation, Professor. So my question is that, so we are a undergraduate university. We don't have GTA. So when we have LA, they kind of know answer, but they don't know the detail of how actually that answer works, or the great physical understanding behind the answer. So how do you co-op with the LA who just took few classes, let's say, like in our case, maybe physics 1 and physics 2, but not the upper level physics, even in the undergraduate, but they are the LA. So, but their understanding, I mean, they do know the answer. So if someone asks the question, they can tell answer, but they don't know the pretty much detail of reasoning behind it. So how can we co-op with that scenario?
Okay, well, we have, like I said, we have a 2-hour lab prep with our LAs. And in that lab prep, we mostly go through the material that the students will be covering the next week. But we also try to ask them questions like, well, what would you ask at this checkpoint? How would you deal with this checkpoint? Trying to get beyond the type of thing you said, where they know the answer, to get at their higher level understanding. So we try this. Now, the truth of the matter is 2 hours ends up not being long enough because they need to review the content and they need to remember that. And it's hard to get questioning in and how to teach and all that kind of thing in. We do now, and this is more recent, we have a teaching, learning, and professional development center, and they are now working with all of the LAs across the university in all the different fields to do a pedagogy class. So now they have that, but the pedagogy class they're running is not specific to our class. So it's good, it does good things, but it would be better if we had more pedagogy in our class. What I have been observing is that when the LAs were taught well as students by questioning, so if we had good faculty and grad TAs and good LAs in the course they took, they learned more about the teaching by being in that class and having good learning assistants and teaching assistants while they were students than our prep. That's doing actually more for them than the prep. That's an observation that I have been making, and I have not done this rigorously, but I think that the way you taught has a very, very big impact on how you teach. And I'm seeing that students who have had good instruction and the way we'd like them to be taught also end up teaching better than students who didn't have such instruction when they were students. So that's just an observation I've been making. Does that answer your question, at least at some level?
Thank you. Yeah, thank you. Thank you.
Oh, thank you so much. Like any other question?
I have another question.
Please.
Thanks, Professor Thacker.
Mhm.
Okay, so if I understood, the inquiry-based method means that there are certain questions designed, and those questions will be asked during the class, and the class is lab related. So, and those questions will be able to cover the required knowledge to the students. Is this the way this technique goes?
The materials are written that way. They have a lab manual that we've written. I could actually share that with you if you wanted a copy. I think I can do that. So they work
Another
through
quick
that
question.
manual. Yeah, and then at checkpoints, there are certain questions, but the instructor, either LAT or faculty member, are actually important because you want to, a lot of times, go beyond the questions that are in the manual. So you want to cover the questions in manual, but you also want the LAs or TAs to be able to ask further questions. I mean, maybe you're at a group of students who are very good and you want to challenge them with a higher level question. You need to know that also. So we talk about the questions in the manual and how to go through that. But then also you need to be able to work with either higher level students or students who get stuck and students who have not correctly answered the question in the. Then you need to be able to guide them by questioning. And that's the hard part, is teaching the LAs to do that. When the students do not have a correct understanding, how do you guide them by questioning to a correct understanding? That's where the LAs are very weak if they've not had physics at a higher level beyond the course.
Quick another question in this part. How many labs, let's say in our traditional lab, we have one lab per week. So it's 16 labs or 15 labs, 14 labs or 12 labs in the course. So how many labs then in this course do you have?
Oh, the inquiry is total lab. You come
Okay.
in and it's not a lab like a traditional lab. I'll have to send you the material. Email me and I can send you the material so you see what we
That
do.
would be great.
It's a total lab. You come in and you sit down with a group and you work through the materials, and the materials are all sets of questions that guide you through this, or say, set up this and try this and see what happens. Or a lot of the materials are predictions first. So we ask them to predict what's going to happen in a certain situation, and then they go and they set it up and they do the experiment. And the predictions are usually set up so that you'll probably get them wrong. Then that's the kind of thing we know from physics education research. So the materials are written with a lot of questions that your prediction will probably be wrong. And the idea is that you set up the experiment, you do it, and you see that you're wrong, and then you have to adjust how you've been thinking about this and come up with something new in your brain, a new model in your head about how this is trying to work. And so all our materials are like this. So it's not like divided into labs. There are sections, we call them units. So there's a unit on static electricity, there's a unit on circuits, there's a unit on magnetism. Well, actually, there's lots of units on magnetism, there's lots of units on static electricity, but they work through these units and they're not like traditional labs. I would have to send you a sample so you could see it.
That would be great.
Oh, thank you. So there is a question in the chat box from Keshav Pokhriyal. I believe Keshav Pokhriyal is a PhD student in physics education research at the University of Alaska Fairbanks. So his question is, did you look at the interest level of students?
What do you mean by interest level of students?
Probably
Okay,
that would
okay,
be if the students are more interested in this inquiry based compared to traditional, where they have to listen the lectures. Just
exactly.
Okay.
This is
I believe
yeah.
Keshav is also on the audience. Keshav, can you please unmute and ask
Yeah,
yourself?
yeah. Like Chandra Joshi sir told that
Oh, okay.
exactly that.
Okay.
Really interesting question. It's mixed, basically. We see this, we have evaluations at the end of the year. And there are students who love it and who buy into it. And you can see it on their evaluations. This is the best course I ever took. This is great. Or students, sometimes they have to take one course traditionally and the other course non-traditionally. And a lot of students have expressed they like the inquiry better. On the other hand, we see the exact opposite also. So we also see students who dislike it, highly dislike it, the inquiry-based section. And what happens is, I can tell you exactly what they say. They say, you're not teaching. This is one thing they love to say, right? It's because we come by and we ask questions all the time, and their perception of teaching is someone stands up at the front of the room and talks to you. So they're complaining that we're not teaching because we don't stand up in the front of the room and talk. So that's a common complaint, that we're not teaching, and there are some others like that. So their perception of what we're doing and don't match what they think we should be doing in the classroom. And this still persists a lot of times throughout the course, given that we started the very beginning. My very first day of class, I jump in to have them working on things, and I tell them at the end of that class, look, this is what you're going to be doing every day. I'm not going to be lecturing to you. I'm not going to be doing what you're used to. So we start the first day telling them how it's going to be, what we're going to be doing, and we do this throughout the course, having this discussion. So in spite of that, we still get these comments at the end that we weren't teaching, that this didn't happen. So we have a set of students who do not like it. On the other hand, I have also seen students who do not like the first semester in mechanics, but they come back and they come back in the inquiry-based class, and it's halfway through of E&M that they finally like it. But they liked it enough to come back, so it's complicated. So we have a whole range of liking or not liking it. We have students who choose it and want it and do not want to go into the traditional section for the second semester, and we have the reverse. So but this is observations and based on, well, on the evaluations that we have. Beyond that, I haven't done any research on it.
Thank you
Thank
so much. Probably we have time. We are towards the end of the hour. Like probably we have time for a couple of questions. Like, do any other questions? Do you have any other questions? Please unmute and ask.
Yeah, I have a few more questions.
Yeah, please. Yeah, Dr. Dongana, please go ahead.
Yes. So by the way, I forgot to introduce myself. I'm from University of Colorado, Denver. So I'm in Colorado, and right now it's snowing here. Kind of interesting. So yeah, I am the one who asked you very first question about COVID period versus non-COVID period.
Yes.
So I like to follow up on that. You said you used, you checked the critical thinking skills.
Mhm.
So what tool did you use for that? What questionnaire?
We were just using the rubric I talked about in this talk. We used our rubric with the Bloom's taxonomy type rubric that we had developed. And actually, we have not compared that to other thinking skills assessments. So that's the one that we use.
Okay, so
Another
okay.
quick question. Yeah, quick question is about the grading system. Let's say sometimes what we do is that, okay, homework is this much percent, attending class is this much percent, lab is this much percent, and then we go up to 100%. And how is that divided into this course?
In this course, homework is 25% because I think that's important. We give a participation grade, which is 10%, which includes coming to class, but also coming to class on time, being on task when you're in class. And lumped into participation is when we run surveys like FCI or BEMA, that's part of participation. So there are things that get lumped into participation. We have 3 midterm exams, which are 15% each, and the final is 20%. And that's our breakdown.
Appreciate it.
Okay, fantastic. So, Professor, from this communication, I realized that Professor Thacker is like easy to get to. But like I see responded so fast to my first email, and so very prompt in communication. Like, so in case you have questions, you can probably send email to Professor Thacker, if I'm correct.
Yes,
Yeah.
that's
Yeah.
correct.
Can we get
Yeah.
her email in the chat, please?
So yeah, I'll share that with with the ANPA group. Let's thank Professor Thacker for her outstanding presentation and answering all questions. So we are now probably we end the session soon. Any last minute thing, Professor Thacker? Are you traveling to Boston for ACT meeting?
I will be in Boston, yes.
Okay, so we'll see there. Like, so I have
I'd
couple
love
of
to see you in Boston.
presentations there, so we'll see in
Yeah, for
person there.
sure. Yeah, definitely.
Yeah, thank you so much.
Okay.
Yeah.
Thank you.
Yeah, thank you. Thank you very much.
Bye.
Bye. Have a nice day.
You too.
Thank you so much. Yeah, so I'll stop also recording.